today I'll be talking about my research in perceptual geometry. In particular, how we're able to use the technique of perceptual geometry to improve compression algorithms for any perception-based media, including images, audio, and video. As a quick overview, in this video, I'll touch on the background and motivation for my research, delve into my video encoder and decoder implementation, and then discuss the implications of this research for the field of compression and beyond. The basis for perceptual geometry is the idea that algorithmic design should be informed by the organization of the neurons in your brain. For the case of vision, certain architectures and layers of neurons represent an image in your visual field. One thing to note about these layers is that they map spatially. Without the spatial representations between each optical neuron, we'd have an extremely noisy experience of vision, as each neuron would map to exactly one point in the visual field. The spatial mapping of an input neuron to these integration centers can be approximated with a Riemannian mapping, which essentially means that there are dependencies between the feature vector elements based on the distance to the central projection. Most Euclidean distance metrics, such as those used in compression algorithms, disregard spatial relationships entirely. To get an intuition for this, let's consider this scenario. Note that the three vectors have the same distance metric when projected into Euclidean space. We can clearly see, though, that the points in vector B are more similar to C than in A spatially. Traditional compression algorithms for visual inputs, like JPEG and MPEG algorithms, make the erroneous assumption that the high-frequency information in an image is the least perceptually relevant without taking into account the spatial relationships between the vectors. The discrete cosine transform is the standard approach for eliminating high-frequency information. I'll present this now so we can understand where the field is coming from and how we can build upon it, given what we know about the neural architectures. Here's how it works. Essentially, imagine a vector of length n which represents n different frequencies of oscillation. It is possible to create an n by n matrix of these different frequencies. For example, this is the 4x4 case, which is what I worked on with my encoder and decoder. Imagine time along the x-axis. As you can see, the top row represents a really low frequency wave, as it has the same value over the course of the time duration, whereas the bottom row represents high frequency. There are large and frequent changes over the course of the time duration. In order to form the transformation matrix, we extend these frequencies into a two-dimensional setting to form the matrix below. Here's a visual representation of the 8x8 case. As you can see, the representation of the lowest frequency two-dimensional waveform is in the upper left, and the highest frequency is in the bottom right. As I mentioned before, though, what we really want is a transformation that represents the spatial relationships between neighboring pixels. This can be accomplished in several steps. The first is to compute a Jacobian matrix that represents the spatial relationships, and you can actually train this on real humans to best model the actual neural pathways. Then you want to add in a potential matrix based on the physical representation of the image, including pixel size and viewing distance. These two combine to complete the Hamiltonian transformation. It is then possible to use this Hamiltonian in place of the original discrete cosine transform. In fact, the discrete cosine transform is a specific case of the Hamiltonian matrix where all Jacobian off-diagonal entries are 0. When you compare the Hamiltonian matrix to the discrete cosine transform for this image, for example, you can see some definite similarities, but note the differences as well. These differences account for the spatial information that is lost in a normal DCT. Now that I've covered some of the theory, let's get into what I did. The first thing to understand is a basic overview of how a video encoder works. In order to reduce file size, there are several frame types: iframes, p-frames, and b-frames. Iframes work just like still JPEG images, but p-frames and b-frames encode the difference between one frame and its neighbors. Luckily for me, both of these frame types use the DCT originally and use the Euclidean distance metrics to compute difference and execute this compression. Therefore, there was a lot of room for improvement. My project was to create a Java-based video encoder and decoder that implemented the spatially aware transformation described above. To do so, I first downloaded the JCodec open source encoding library and tweaked the H.264 encoder and decoder to include a transformation matrix of the DCT that I derived. I wrote a MATLAB script to accomplish this and used the images C package to verify my results. The final transformation matrix looked like this, and the visual representation of it looks like this. You can see the parallels between this and the 8x8 case. Compared to the original in-place DCT implementation, the video output was the same when the input macro blocks were transformed using my transformation matrix. Now that I had the transformation in a matrix form, I could start to play with it and change it to represent the Riemannian projection. In particular, I had to compute a Hamiltonian matrix that would represent the similarities between independent vectors in the macro blocks. I computed a Jacobian and a potential matrix based on the physical representation of the image, then used these to create the Hamiltonian matrix and replace the DCT with this in both the I and P frames. And here's my result. The differences are quite subtle, yet they reliably lead to small but very consistent improvements in the encodings. So, what next? One of the first things to quantify is how well my encoder and decoder perform compared to the MPEG case. Since I already have an MPEG encoder and decoder working, I'll be able to generate similar output files and verify them against human test subjects. Characterizing how good a certain compression algorithm is requires several metrics. Human reported represents the perceived difference between an original image, and entropy represents the description to the file size. Comparing these for the two videos, we can obtain an idea of how well the perception-based encoder performs. Also, as I mentioned before, there may be room for improvement in tweaking the Jacobian after training on human data. We can use a gradient descent algorithm to maximize perceived quality for a given file size. My lab has done this for JPEG case already, but it'll be really interesting to explore how we incorporate feedback for a time-sensitive input like video. In conclusion, the implications of this project are massive. We've detected a flaw in the way we treat perceptual inputs, and it has the potential to change compression on a colossal scale. Improving lossy compression has countless applications, and so one of the most exciting things about working on a project like this is that we can't even predict the impact of our work. For large files like movie theater videos or AI training data, we could see vast improvements in the size of architecture needed to support these files. Even though individual improvements are small, these compressed video files are used billions of times per day. Modest individual improvements can add up enormously. Thanks so much for listening to this presentation on my research in perceptual geometry. I hope you learned something and are as inspired as I am every day by the incredible combination of modeling computer science on the human brain.